we were discussing logistic regression and in particular how to fit the model, how to do it in PyTorch. We went over the code, and we also introduced the idea of gradient descent with momentum. So the loss for logistic regression problem is convex, but it's trickier than the loss, like the quadratic loss. So there's this exponential, there's this log loss, which if you recall. So because of this log business, things are not as straightforward. So the momentum idea helps speed up the convergence a lot. And then we also saw issues with like potential divergence. So if you don't do the step size and the momentum right, then it could diverge. But for a good like range of the step size, also known as the learning rate, and the momentum parameter can converge. We're going to explore these ideas more. So what I want to do is extend this to multi-class classification a little bit. This is basically what most of the current machine learning sort of algorithms try to do multi-class classification, and in particular, large language models, which most of you have heard, like ChatGPT, and the general line of work. So they're basically doing multi-class classification. And hopefully we'll talk about that at some point. So in order to be able to do that, also like traditionally, let's say, like two classes is good if you're trying to, for example, detect a disease or not, like an email is a spam or not. But you want to have more classes. Let's say if you do vision, you want to categorize different objects, not just two objects. And so but once you do like multi-class classification, things become more interesting. Okay, so the plan is to extend to multi-class classification first. That's one possible extension. The other extension is to go away from like the linear models to more complicated models. So we started from like the more complex possible models, like the local averaging, they fit anything. But then we restricted ourselves to a class of linear functions or linear subclass. Maybe at some point I'll ask you why we did that, but it's important to know why we did that. But then we also now want to extend further. So we started from very general, restricted to a very restricted class. Now we want to extend to more general, but still parametric, still like control. So that's the other extension that we want to do. And that leads to like the idea of neural networks and stuff like that. Okay, so multi-class classification on nonlinear parametric models. These are the things that we want to do. So we write it down. Extensions, multi-class classification, and two nonlinear parametric models, and then ChatGPT. Okay. So like few steps for me to speak back to just wanted to motivate. Okay. So sounds good. So what is multi-class classification? What is binary classification? So binary classification, the idea is that we have X, right? And then we have Y. And I'll learn a mapping from X to Y, where this Y is binary, X could be general. So multi-class classification, it's very similar. So we go from X to Y, but now Y is like, I'm going to do like 0, 1 up to C minus 1. So they're C classes. Okay. I'm going to introduce this notation. So this is, so for like an integer, let's say C, this is like 1 to C. This is very standard. If you see like C in bracket in papers in statistics, machine learning, optimization, being integer 1 up to C. But I'm going to use this notation, which is my own. So take it with a grain of salt. This is not standard. I'm going to use it for 0, 1 up to C minus 1 to avoid writing this every time. Okay. So the reason why we do this because PyTorch is zero-based, so it's easier to work with the zero limits. And it also naturally is sent to like binary classification, because if I take C equal to 2, you can take it 0 and 2, right? Rather than 1. So class labels are 0, 1 up to C minus 1. So that's the only difference, basically. We have more labels. Okay. So you still get the training data. So you're still like the assumption is that we have like X and Y pair, generic pairs from a distribution. Not a distribution, it's the joint distribution of a pair, which is from X and from that space Y. And then you observe training data and so on. But I want to basically impose a parametric model which leads to sort of linear decision boundaries. Okay. And so binary classification with linear boundaries. So that was like an example was the logistic regression. I just have to specify this conditional distribution, right? Sigma theta transpose X. So that was our specification of binary classification with linear decision boundaries. You can change sigma, it wouldn't be logistic regression, but anything in this ballpark of this formula is going to give you linear decision boundaries. So how do I extend this? So in multi-class classification, it's not enough to just specify the probability of Y equal 1 given X. So the reason why we could do this is because you just have two probabilities for Y and it's not 2. Okay, in this case, you have C probabilities, so probability that take Y takes a value 0, 1 up to C minus 1. And they all have to sum to 1, so there is one constraint. But at least I have to specify C minus 1 possible functions. So if you think of this, I can write it as, let's say P y1 given X is equal to X. Let's say do this. So this is the general form. So it's like a parametric function of X. So G theta of X in the binary classification would be sigma theta transpose X and 1 minus sigma theta transpose X. And this Y in this case takes values 0 to 1. So my vectors are 0 index based on 0. So when I put Y equals 0, right, so basically G theta of X, the 0th coordinate would give me sigma theta transpose X, and G theta of X1 gives me the second coordinate, right? So the first is this, right? The second coordinate is the other guy. Okay, so in this way, I can write logistic regression in a way which is like a little more general, right? So you don't have to say I just specify 1, this specifies both, and you can see they sum to 1. So the constraint is that the coordinates of G sum to 1. And so just G is mapping from X to basically a vector 0, 1 to the 2. So these are probably the coordinates. So this very much extends to multi-class classification. So if I write it, is this clear? Yeah.
I'm just trying to, what's the 0th coordinate, what's the first? Because like the way we really P capital Y equals lowercase y is G theta of X with little y. So like in the two class case.
So this G theta of X is a vector. That's two coordinates.
I follow that. I'm just trying to understand why like the first coordinate, which gives us the probability y one, is the one that's up top.
That was not correct actually. So you're right. It should be the other way. 1, 0. Good. You have to do the other way. Okay. So you seem to understand much better than me. So 1 minus sigma theta transpose X.
Okay.
Right? Now works? Yeah. So the other way. So the 0 should be like the probability of 0. I could have written y minus 1 minus 1. Good. Wow, very good. So this very much extends to multi-class classification. I just can write this formula, right? Just assume a parametric form. There's just some parametric form here. And then y, but now y is in that C star. Okay, so it takes these values, and this G is going to be just some function. So G theta X 0, G theta X 1. So the coordinates tell me the conditional probabilities of different classes. So we haven't done much here, right? But this gives me the general form of a parametric multi-class classification problem. I just have to specify this conditional distribution. And you know that once we have this conditional distribution, we have the optimal rule for this model. The optimal rule is going to take the first classification error, basically. So it takes this and minimizes or maximizes the class probabilities for any x, the y that maximizes these coordinates. Okay. So among the coordinates, the y that gives you maximum value is going to be the optimal decision. So then I have the decision boundaries. So the main thing is specified in G theta of X. And I want a function that sums to 1. Basically, it produces a vector that always sums to 1. Otherwise, I'm free. So if you think about it, or there are many functions like, right? If you want to extend this, right? So what this is doing is, if you remember what sigma was, this is like, I can do basically e to the theta x divided by 1 plus e to the theta transpose x. And then 1 plus 1 e to the theta transpose x. Okay, so that's the form of the logistic. So if I plug in sigma, it would be like e to the t divided by 1 plus e to the t. And so that would give you that, and the other this. So you can see it's like, you can think of this as e to the 0. So I'm basically taking the applying e pointwise to this vector, right? This gives me a e to the z and e to the theta transpose x, and then I normalize by the sum. So the punchline is that this can be extended. So you can think of a function that takes a vector, let's say u, and maps it to, let's say, EU0 divided by the sum, EU1 divided by the sum of EUI, let's say. It's a little bit difficult to write that. Okay. So let me write the function this way. So this function, let's call this softmax. There's this function that, okay, this function takes, let's say RD, and maps it to RC. And so it takes a vector actually not C. Takes a vector in RC and maps it to RC. And the way it does it is, let's say the y coordinate here is going to be, so this takes a vector, is going to be e to the u sub y divided by the sum of all the ui's, I from 0 to c minus 1. Okay, so for example, if c is 3, what it does is, so we're applying it to something like u1, u2, u3, and it creates a vector EU1 divided by EU1 plus EU2 plus EU3. And then the same thing, But now here we have U2, and here we have U3. Okay. So it raises the vector to like e to that coordinate and then divides by the sum of all the coordinates. Okay. For example, if I do c equal to 2, I get s, let's say applied to 0 and u1, for example. This would give me e to the 0, right, which is 1 plus e to the u1, and then this gives me e to the u1 divided by, okay, should have been, to be consistent, 0, 1, 2, 0, 1, 2, and then 0, 1, 2, 0, 1, 2, 0, 1, 2. Right, okay, so you get E1, so the softmax applies to 0, and this is giving 1 minus sigma U1, sigma U1. Okay, so this gives me the kind of output that I need for the legend situation. And so this gives me a general blueprint to map any vector. This actually maps from I would say the space of probabilities on C. So from a general vector in R to the C to the space of probabilities on C, which is the space of all possible vectors P0, P1 up to PC minus 1, such that let's say Pi is bigger than or equal to 0 and they sum to 1. So it's a general function that allows you to map any vector in RC to a probability vector in RC. Better right here. It's P0 up to PC minus 1, such that Pi is bigger than or equal to 0 and summation I from 0 to C minus 1, Pi is 1. Space of probability vectors on C. Yes.
So we're just taking like U sub Y over, does it have to be E to the U? Because we're trying to map to a probability space. So
yeah,
like what it maps to should all be between 0 and 1, but
right. So this makes it positive, right? So you want it like to give me potentially negative. So you want something which is positive and also has 0. So e to the that takes the positivity nicely, and then you divide it by the sum. This takes there. Okay. So I don't have any. That's the cool. The cool thing is I don't have any restrictions here. So you can have a general vector invariant with massive probability. If you think about this, but it has to be like from U like C to C. Right? It's not like 1, 2, or like I don't know. So it's like on the same space. So if you yeah.
Is there anything special with raising it to e power? Like if we only want to make it positive, we can also square it and still get
Yes,
some good
you're
way.
right. Okay, yeah, I can square it. And actually, yeah, you could have uy squared divided by the sum. That would have worked. Yeah, so this is not the only reason. So it's easier to work with because of all the nice things about the logs and interactions with, for the same reason why this was useful. That's actually a good point. There's no specific reason why we need like sigma here. So anything that maps, for example, monotonically from negative infinity to infinity would have worked here. It would give you linear decision boundaries. So any basic thing in CDF. CDF, the functions that go from negative infinity. So at negative infinity, they're 0, and then at infinity, they're 1. And monotonic increase, and then we have the same kind of decision boundary. People, for example, use like the CDF of the normal distribution here that would be coded because use it. But this is very easy, like the differentiation is easy, and it interacts nicely with logs. When you take the log likelihood. Yeah, so this is not the only reason. But it would be fun to try. Let's say, okay, so it's like a suggestion. So you were like, your name was Narine, right? So Narine sort of estimator, or like, you know, we can coin the name. So I don't know, Q of U maps to uy squared divided by sum of 0. This would do as well. You can write a paper, probably publish it somewhere if it turns out that it works well. But the cool thing is we can just implement this in PyTorch, see how it compares. But this needs to satisfy the condition, right? So it has it produces some probability that it will be non-negative, and there is another interesting feature, which is, I don't know, so we have to think about this. Work. There's another nice feature of this is how it acts on shifts, which is so the thing to notice is because I'm introducing this constraint, there is no one-to-one mapping. So this mapping is not one-to-one. So there's potentially two vectors that go to the same thing, but because of this normalization. But if you think about this, it becomes clear if I add, for example, a constant shift. So for example, add 2 to every coordinate, I get e to the, for example, u0 plus 2, which would be a factor e to the 2. This would have a factor e to the 2, this would have a factor e to the 2, and all of the terms in the denominator would have e to the 2, and it's canceled out. Because if I add a constant vector, or like a constant value to every coordinate, it doesn't have any effect. So it's sort of shift invariant. This one doesn't have that property. Right? And so so this we have to deal with because there's a constraint on the output, which is not on the input. So there's like 1 degree of freedom less here than in the input. So they have to sort of the map has to be non-one-to-one. But modulo that, like you assume that it's almost one-to-one. So if you identify vectors that are shifts of each other, then over that space, it's mapping that class to distinct object. Those classes to distinct. Okay. So now how can you use this to define the model? So my original X is, let's say, in RD. I will have to put it in RC so that I can apply this softmax. Okay, so the input to my model is in RD, right, X. I have a softmax operation. Let's call this softmax block that takes something in RC and produces a probability vector, which would be the end result. Okay, how do I deal with this? Okay, to go from RD to RC.
A linear combination.
The linear map. So this is what people in deep learning or neural networks discovered, that if you want to like change dimensions, the easiest thing is like to do the linear map. Mathematicians also know about this. So if you want to like pass information from one space to another, the dimensions are different. The simplest thing you can do is like have a linear map from that space to the others. So the linear maps are often, how do you specify a linear map? What? Theta transpose. So here is a linear map from RD to RC. How can I compactly represent? How can I compactly represent like a linear map from RD to RC?
A matrix, right?
A matrix, yes. So the easiest way to do is like a matrix, which I'm going to do as theta, capital theta. So this matrix has to take vectors from RD. So this side has to be RD. Sorry. This side has to be RD. Because it gets multiplied by, so this has to be d-dimensional. So rows get multiplied by, so d is bigger. So this is d, gets multiplied by a vector x in RD. Right, and this side has to be c. So c rows, d columns. So if you multiply your c by d matrix by d by 1, you get c by 1. Okay. So that's how you easily transform. So if I have this theta, basically theta transpose x would do that. And then I apply softmax. I get my probability. Okay. So this would be a softmax regression. Y equal y, given x is equal to x, is equal to the y coordinate. Okay, so this is in RD. This is in RC, or like RC, or better, like probability vectors on C star. And so the output is, sorry, this is in RC really. This is in RC. And this one is in probability vectors on C star. Yes.
So at the beginning of class, you were saying today we're going to extend logistic regression to multi-class classification, but stay in the parametric world.
Yeah.
And I'm just, this is not multinomial logistic regression, right?
It is. I mean, statisticians would call it multinomial logistic regression. Like up to like maybe like a little bit like if you account for the intercept, like there's some issues, but this is multinomial logistic regression.
Oh, okay.
Yeah. Also called softmax regression. The same thing. Yeah. So it's parametric and it's also sort of linear. It's both parametric and linear, right? If that's the extension. Yeah, so if you know this is an example of a generalized linear model. So statisticians would have no problem with it. It's often called multinomial. I don't know, multinomial logistic or multinomial regression, I forgot. Do they call it multinomial logistic? No.
It's just what I'm familiar with. I was going to square this with.
Yeah, okay. Either this or multinomial regression or logistic regression. Yeah. So maybe logistic regression would be good. I forgot what the name is, but yeah. Softmax. So multinomial because So this is like a multinomial, but it's like a multinomial with one observation. Basically categorical. But if you call the first one Bernoulli logistic regression, then this is multinomial logistic regression. So this distribution is multinomial of one. Right, so you can say this is, so in the logistic regression, we had like this is equal to like a Bernoulli, right? Blah, blah, blah. Here we have this is equal to, like the distribution is a multinomial one and this quantity. Yeah, y given x is equal to x is multinomial with one observation. This is probability vector. Okay. All right, if you want, I would write it as categorical. S theta, just one observation. Multinomial usually. It's interesting when you have multiple observations. It's just one observation. It's basically a vector. So what it does is every sample that you give me, so this goes to the encoding. I should be a little bit more careful. So this is the limit the way I wrote it. Yeah, this is fine. Is it fine or not?
I'm sorry to distract.
No, this is good. Because the thing is, so here, y is just a label, like from 0 to c minus 1. Oftentimes, if you write it like this, you're thinking of y as a vector, with the so-called one-hot encoding. Okay, so I think, okay, yeah, so I have, this is all like notation and convention, how you treat, like you can still think of this as a label, or you can think of it as like a vector. So it's going to be 1, 0, 0, 0, or like 0, 1, 0, 0, or all the way up to 0, 0, 0, 1. Okay. So at least in the way I think of this as multinomial usually is the way. And it just, for example, if it's n, like each row, each element, we count how many of each class I observe. So for example, I do like multinomial p and, sorry, n and p would be a vector. So multinomial like 10 and p, then if I draw, for example, y from this, then I would get something like, for example, 3. Maybe p would be like 0.1, 0.4, 0.5, right? 3 classes. I may get, for example, I don't know, about 1 here, maybe 4 here, 5 here. Okay, so let's count how many like, I'm going to see here 10 observations, 1 in class 1, 4 in class 2, and 5 in class 3. Maybe next time I get, this is random, right? 3 here, 6 here. Okay, and maybe sometimes I get like 0 here, 4 here, 6 here. Yeah, something like all these possible combinations. So if I do this, I'm thinking of, because there's just one observation, there's just going to be 1 here. They have to sum through the number of observations. So this gives me the same information as if I encode by label, but this is called one-hot encoding, and it's often useful. Hot encoding in applications. Okay. Let's see. These are all good points. Okay. But the model is the same. So whether you encode it like this or encode it as a label, it has the same information. So you can encode the same categorical information in a different way. The funny thing is, if I write it as categorical, I'll still think of it as a label. So that's just a distinction. Is that clear? Sure. Yes. And one-hot encoding is good too. It's a one way of encoding. This is not the only way. Yeah, it's different. ways of encoding. So if you've seen like the statistics book and regression, right? Or like take one of the C, for example, this encoding is used. There are other encodings as well. These are sometimes called boundary variable. So if you want to encode a categorical variable and put it in regression, that's one way of encoding. So we don't have a binary. Yeah, so let's not go there. But if you do, for example, want to do like ANOVA, like 5 groups, you can write it as a regression with these kind of categorical features. Okay, sounds good. Okay, so this is the model, right? So how do any questions about the model? So this nicely generalizes. Forgot it is our problem, but we can try to figure out what the decision boundaries are. What is the optimal Bayes rule? The optimal Bayes rule here is, or the optimal rule, or the Bayes rule. Once you have this model, the optimal classifier does what it often does, which is take the argmax, right? So you f a star, for example, of x is going to be argmax p of y equal y, given x is equal to x. And now y belongs to this class. Okay, so for every x, I'm going to go take all the elements of this vector and pick the coordinate, the index, which gives you the maximum value, and that would be my prediction. And it becomes a little more complicated, but I'm going to show you the plot in code, but you can verify what exactly are the decision boundaries. The decision boundaries are still linear, but there's not one decision boundary, okay? Because you have multiple lines or hyperplanes and they intersect. And so the intersection is defined in cells that define the optimal class. Okay. But the issue is that the decision boundary is between 2 classes of data. So it's still like one hyperplane or one line separates 2 classes, but now you have multiple classes. So you separate these 2 classes by 1 line, these other 2 classes by 1 line, these other 2 classes by 1 line. And in the end, one class is differentiated from all the other neighboring ones by multiple hyperplanes. But things become complicated. Okay? The shapes would become more complicated. Different types of things. Right? So Bayes rule is, and then there's this same notion of idea of noise. So if I increase the size of theta, it's gonna. So if I shift theta, basically. So okay, so there are a couple more things to remember. One issue is the so-called identifiability. So this parameter theta is not identifiable. What do I mean by that? Anyone knows what identifiability means? So there are different values of theta that give me the same exact model. Okay, and that the reason is that softmax is invariant to constant shift. And maybe this would be a homework problem, I believe. But what happens if I do something to theta such that the effect is just adding constant shift to theta times x as a result. Okay? And if that's the case, then for example, let's say I add something to each row. So let's say I add a vector, right, to each row. Let's say vector b added to each row. So when I multiply the previous row times x is doing something, plus v transpose times x, right? And the same goes here, the same goes there. So this v transpose times x would add to every coordinate, right? And because that's the constant shift, that's going to vanish when I do the software. So the rows are identifiable up to like a constant shape. And that's a little bit problematic. So whenever you have, so this parameter is not the exact, so if I have like a vector to every row, this will give me the actual probability model, so I can't identify them from data. I can't even identify them in the whole population. So you give me the whole population, infinite samples basically. I can't be distinguished. So that's the issue of identifiability. Okay. So different parameters that you need exactly in the model. So we have to be content with that. Okay. If your goal is to recover, then you have to specify a particular condition. So maybe I'll set the first row to 0. That would let down. So this is very similar to what we did, for example, in logistic regression. So I'm pinning the first coordinate to 0. I can allow the two coordinates to vary, and then things would wouldn't be identifiable. So I just need to specify. So for example, like I say, I'm gonna force this to first row or like last row or whatever, 0 or something, then the rest would be identifiable. But if you don't care about the parameter itself, as in this course, like I said, it doesn't care about the parameter like top all. You can estimate it. If you don't care about the parameter, you just care about the this functional form. You care about the value of the probability because that gives you the prediction. So for prediction, everything is fine because you get a different parameter, but it gives you the exact same prediction. So for that reason, you're not going to worry about that. But this comes up when you try to do optimization as well. When you try to do like inference on parameters, if you're such, you have to worry about identifiability. Right. So that's to get enough points. So everyone happy with it. It's an important issue that is whenever you write a parametric model, and if you care about recovering the parameter, you have to make sure that the parameters are identifiable. Otherwise, you have to impose constraints enough so that you pin down a particular one that then you can say, okay, this one I can identify. So identifiability, that's one issue. So we talked about like linear decision boundaries, optimal rule. These are known. Like we can easily do that. So the issue of noise. Okay, so the noise. Again, the same kind of idea happens here. In that they can like control the level of noise by the scaling data. And that's the way I won't see them. Scale. And the last one is like how to fit, or how to train / fit / learn the model. So how do we do that? What I need to do is like have a training data, I need to learn data. And I've specified the model. I haven't opened that. Sorry? Maximum likelihood. So we can do maximum likelihood. That's one approach. MLE. The natural approach. So I have to write down the MLE. So this is, again, I can do like log likelihood. We will have the product here again, PF, YI, theta given XI. The same sort of factorization happens because we're working like conditional on the X's and conditional on the X's, Y's are independent, and I have this. And this particular quantity in our case is just S theta, now XI, and then the YI coordinates. Okay, that's just what it is. Okay. So you add XI through theta, and then S. This gives me the whole probability vector. So I just observed the the ith one, so that's the probability of observing y either things. So if I want to minimize the negative log likelihood, so this gives me summation I from 1 to n, negative log s theta xi yi. So we minimize this over theta. And let me give this a name. And you can see the log interacts nicely with the softmax. So these are e to the something. And if you do, you don't need to do the, I'm going to write L. This is really a log loss, but again, because people in machine learning call it cross entropy, I'm going to write it as cross entropy, loss cross entropy. Y and Z, let's write it as negative log S Z Y. So let's define this loss. It is defined between a vector which is in R, which is in C, like a label, and something which is in R C. Okay, so it takes something in RC, which in our case we interpret as logits. So the equivalence of logits in logistic regression, and then this is the label, and then this forms this loss. So it takes the softmax of Z, would be a probability, looks at the y coordinate, and then takes the negative log. Okay, so this defines a particular loss between a label and a logitic. Okay, and then this loss I can rewrite this as okay, I can do like maybe usually the 1 over n, doesn't change the minimizer. So 1 over n summation I from 1 to n. LCE cross entropy yi and xi. Oh, sorry, theta xi. So we essentially absorbed again the softmax into the loss. So now I have a vector nonlinear loss, but I'm applying to y something linear here. So this very much looks like this is an ERM like looking formula. Okay, so we're back into empirical loss minimization, empirical risk minimization, very minimal difference from linear regression for quadratic loss or logistic regression. So linear regression is quadratic loss, like logistic regression was like log loss, and this was a theta transpose xi, and this is just generalization. This you could call log loss, it would have been called log loss, but really people call it cross entropy, so we have to do that. So there was a binary cross entropy where it was between categorical language and probabilities. Okay. So we could have done that. So you could have like this would be negative log of p, for example, here. But if you go back, you can just identify. And the unfortunate thing is the names are not consistent. So we're going to work with this, which is, yeah, they call it like multivariate version of the log loss or cross entropy. Okay, so I can minimize this. How do I minimize this? How do you minimize? Gradient descent of machine learning work, or gradient descent of momentum. This loss is also convex, so you can convex yourself. And even if it wasn't convex, we could still do it, but that's the same machine learning, just change the loss, change the, so the model now here is just a linear model. So my model is just xi goes in. There's this linear model that maps RD to RC. And then here the output is, I can call this, let's say ZI if you want. These are the logits, I pass it to the loss. So the model is really a simple linear model. The rest is like taken care of by the loss. Sounds good. So what we do is import torch, and n as an n, so that's the model import. at this point, we're not doing much neural networks, but we're going to use the NN module thing that you have to remember. I talked a little bit about that, much more. And then, of course, and then we also import functional as F. So this is a different way of importing things. So it's like storage.nn.functional, but I'm calling it that. So this will have, for example, the softmax. We could have implemented ourselves, but I just want to show you. So here I'm creating a torch tensor, right? And the double bracket here, as you see, is going to create, what does it do? Like the double bracket. Yeah, so it's like the outer one is saying the row. So I have a list of rows, and then within that list, I specify different rows. So just one row, and that row is 1, 0, negative 1. And this is also a trick. So I'm putting one dot. So this is like a floating point. So I don't have to specify the float type because one of them is like float. And the type would be very float. So this dot is important here. Otherwise, it would be an integer tensor. And try to like specify the type, right? D type. So 32. This is like more explicit. It is always good to be more explicit when you do programming. This is a tricky thing, which is not curriculum. Okay. I'm lazy, so I'm going to do that. And then x plus 0, we'll see, like I'm not adding anything to it. So if you do this, you can see E type flow is a tensor, shape is 1 and 3, okay? So it's one row. And then I apply softmax, f dot softmax x, along dimension 1. Okay, dimension 0 is the rows, dimension 1 is the columns, so it applies along the columns, which is what I want. What I want to apply on this. So this is like a 1 by 3 matrix, so 3 columns. So I apply basically 3 columns. And this is going to do e to the 1 plus e to the 0 plus e to the negative 1, and then divide by the sum. And so probably you're good, you probably can do it in your head. I can, but you can just imagine this should be higher, this should be lower, and this should be really low. And so they sum to 1 and gives you a probability. Right? The key is like if I add like 5 to everything, right? So this changes, but the softmax doesn't change. Right? So it's invariant to shift. Right. Okay. We could have done something which is, so for example, I do 0, 0, what I would get is, did I get correct? Okay. So 1, 0, 0, so I have to do like negative infinity if I want to like get a, infinity is not going to work. Does torch have infinity? Yeah, I forgot. So in any case, it's hard to come up with the numbers that you can read, but you have to like raise e to the power. But okay, that's that. And then, so this is clear. So f dot softmax, it can operate on different dimensions. Now, how do I create a linear model? So that's where this NN comes in. So NN module has like a linear layer or linear map defined automatically, or like predefined. So it's like taking 2 inputs, output is 3. Like the input is 3-dimensional, output is 3-dimensional. Okay. So it's really a matrix from, it's an operator from R2 to R3. That's really a matrix if you think of, which is, has 3 rows and 2 columns. Okay. And it's a little more than that. It's not just a matrix, it's really an affine map. So people who designed this really didn't care much about like mathematical preciseness. So it's not a linear map, it's an affine map, which means that it has this. So it's like plus intercept. Okay, so it would be like W times X plus B. So B would be the intercept. So that would be like called biases, weights and biases. So first I created, you can say linear layer in features to out features tree bias to. Bias means that constant vector added. And then you can see, so there's the weights. So in that weight, this would be a type parameter, and dot data would be just the data of it. And then lin dot bias, the data, and you can see the different things. So it's like the weights is a 3x2 matrix as we expect. So it's like W times X plus this vector, which is going to be that's three-dimensional, but three-dimensional vector. So it's a 3x2 matrix and a three-dimensional vector. So this gets multiplied by something which is two-dimensional, but use a three-dimensional vector that's added to it. W X plus B. So this is the basic idea. So if I do the like bias false, for example, probably I can do bias false, then probably there's no bias, which is there. Okay, doesn't even have a bias anymore. Okay, we'll have the bias. So if I do just lin that weight, you can see it's a parameter containing this tensor. That data extracts tensor. So this is a class parameter. And parameters have interesting features. Okay, so it's like gradient requires grad is true, and Python keeps track when you create parameters inside the model, keep tracks of the parameters. So when you say parameter, after the parameters of the model, anything that's off that parameter is it's gonna give it back to you. So it's good to know the distinction between this and so I can sort of, this might not be the best way, but I can redefine the data. The parameter I want to make, so this is random. So when you generate one of these, and then the linear, it randomly populates the weights. I forgot exactly how, but some variant of a random distribution. Maybe Gaussian, maybe you have to check the documentation to see what kind of initialization they use. And this is a huge, like different initialization, people use different initializations. I'm gonna have like economics of different ways of explaining. But this seems to be like something that potentially like it's agreed upon by the majority of people, so it's a default. And now I want to change it, so I'm just I have to specify a 3x2 matrix, which I'm doing like 1, 2, 3, 4, 5, 6, and a different bias. Now I can look at these two, and then you see they have been changed to what I want. Okay, so this is really implementing Wx plus B. Okay, so now how do I apply it? I'm just like, treating it as a function. So lin, okay, so lin is my linear layer, remember? So this is an instance. Well, what I created is an instance of that in a linear class. So now this is an object of itself. I can apply it to vectors. And when I apply it, it just does the evaluates, right? So this is going to be this is going to be a 1x2 vector. And the way these NN modules apply is they apply row-wise. Okay, so it's going to apply to each row, right? Separately. Applies the functions to each row separately. And so for example, if I do what? If I do 1, 0, you can see it gives me another one, which is the output on this vector. Okay, so this is going to be a 2x2. Let me do another one to see, make it more clear. 3, 1, 0. So it's going to be 3x2. It operates on each row, and we treat each row separately as input. So each row will be two-dimensional. This matrix gets multiplied by that vector. So for example, let's take the second, and then each row like is going to be output. Each row is going to be output and then the corresponding rows. So for example, this one, 1, 0, when you apply it here, it's gonna pick the first column. Right? So it's matrix multiplication. This matrix times 1, 0 would be the first column, 1, 3, 5, and then I add 1, 2, 3. Okay, I get 2, 3 plus 2 is 5, and then 5 plus 3 8. Okay. The last one is just take the second column, add this 2, so you get 3, 6, and 9. Okay. But first one you can do probably as well. So you get 1 minus 2, so you have to get 1 this column minus 2 times that column plus this that would be. The thing is that these operate on rows, on the first dimension, on the 0th dimension. And the idea is that the 0th dimension represents the samples. Okay. So I collect all the samples, I just store them in rows. Right. So this is like a design matrix, what they call batch, or like samples. And so you operate at each sample separate. They can just input the entire sample as a matrix, sometimes a tensor. So the first dimension, the 0th dimension, always is reserved for the batch or the sample. Is this clear? So for example, I would get an error, I think, if I do, probably wouldn't get an error. If I just do this, would it work? If I just do, let's say 1, 0. Oh, this is the issue with that. So this would work. So you can still pass like a vector. And this would work. And you can also do this is also going to work. So it gives you, if you pass it a vector, it gives you a vector, right? So you can see just single brackets. If you pass it like a matrix, it will give you a matrix. Okay, so the mechanics are sort of clear. Okay, so this happens for all the possible, like anything that you drive from this module, that's how they operate. And the way that it's implemented is implementing that forward method that we saw before, and we'll see later. So the way it works is, so this is the same idea. So you apply it to multiple rows, and it gives you like multiple outputs. And it's equivalent to doing the forward. So when the forward applied to, in this case, for example, that was the vector, the second with this. So I'm applying it to the matrix, which has row 0, row 1, row 2. X2 is just like takes the second row, like 0, the third row is. So this is also something which is quite interesting. So it picks the row of the matrix. Okay, so it would be that. And okay, so these are all like different ways that you can apply. And it's also equivalent to what it does is really the transpose of this wave on this side of X. So because you're applying it to rows, you can think of it as transposes of the X's. So the way that you apply it to each row, so I want like W X plus E. If I transpose it, it's like X transpose W transpose. And if I store the X transposes along the rows, I can just multiply that matrix by W transpose. So the operator is X times the transpose plus main by X. So this is going to do the same thing. Okay, so this is the same as this one. Yes, I can verify that doing what you expect.
So X is always a row, right?
Sorry?
X is always a row, vector, it's not a column.
Usually it's either a row vector or just a vector which has dimension 1. Like it's neither a row or column.
Okay, but you cannot multiply it after the matrix, like W times X.
I can do it, but the way that these work, I can do lambda times. This would also work. If X, so here X is a matrix, right? So this wouldn't work. But if it's like a vector, you can do anything that works mathematically. That's fine. But this linear, if you want to apply it, like if you do want to do this, which is what we want to do in X, this has to be like n by the dimension of the input, or just a vector of dimension n. That's how it works. And this also verifies that this is equal. Interesting. Okay. So softmax. So now I'm going to go back and define my softmax regression. This is the class that I'm defining here. Inherits from this NN module, so it has all the functionalities. And then it has, again, often like an initialization and a forward pass. So initialization initializes, so it takes self, which is going to be always the first element that it passes, is going to be the object. When you call it an object, it's going to be the object itself. And then input dimension, output dimension, I'm going to create a linear layer with input dimension, output dimension, and store it in self.mean. Okay, so this path will have this one, and this would be a parameter. This would be a layer. It contains a bunch of parameters, like the weights and the biases. But this linear self.linear is going to be my basically stored at theta x or w, not theta x, w and b. Encapsulated into this linear layer. And the forward pass, if you give me x, what I'm going to do, I'm going to apply self.linear multiplied by x, and then do softmax. And so this gives me the output of the softmax. Okay. Along dimension 1. So it's going to be s theta times x along, and I do the softmax and doing along the causes. And so the second dimension basically. So let's do this. So I'm gonna create the model goes from 2 to 4. So input is 2-dimensional. 4 is obviously 5 classes, but 4 classes. Right. So the output dimension here is going to be C, the number of classes. Seems like 4 classes. And so I'm going to list the parameters. So true model is going to be a model that has less parameters. So it's going to be parameters. It gives me a generator, and if I make it into a list, it gives me this. And then you print it, and you can see the parameters. It has this parameters, this and that. These are the parameters of the linear model. Okay, so whatever layers you create here. So this has 2 parameters. These are registered parameters of your object. Okay, so you have more of these things. All of those parameters are registered. So when you do, like, let's say true model dot parameters, it outputs all those parameters. I can also do this. I can loop through. So if you just do it, if you give you a generator, it's not going to give you some other nice things about Python. So if you do like true model dot parameters, it's like a generator object, which is something that we can like move through and extract parameters out of. If you make it into a list, it would produce all the lists, but usually you have these generators and you loop through. So for every parameter in true model, I'm going to multiply the data by 10, for example. That has the effect of multiplying that data by 10, it would increase the, like, apply the noise. So I started from like these parameters, you can see. I'm printing it before the loop, and I'm printing it after the loop. You can see like they're all multiplied by 10. So these are the parameters original, these are the parameters that are multiplied by 10. This would allow me to control the noise. And so now I'm generating from the model. So how do I generate from the model? I generate x's, okay, so 2000 points, generate the random normal 2000 by 2, apply true model. Okay, so this gives you the probability for every row. So the probabilities would be 2000 by 2, and you can see probably 2000 by 2, and these are the probabilities. The probability vector for every sample is a 4-dimensional, and then a sample using a multinomial distribution, or categorical really. So the torsion distribution categorical, I pass the probabilities, and then sample. Okay, so samples for me the Y's and this would be 2000 labels. Okay, so no, okay, so let's look at the okay, so what is this Y class? So this is the argmax of the problem we had like the first time. So these are the optimal labels. These are the true labels. So distinction is optimal labels, true labels that are noisy. These are the actual labels that you see. These are the labels that optimal rule things based on the probability. So if I do the plot, so this is plotting the Y class, which is the Bayes labels, and this is the true labels. Okay, so you can see the Bayes labels, they're pressed and they show you the boundaries. So the boundaries are exactly, so this is like the boundary of these two classes, this is the boundary of these two classes, this is the boundary of the green and the blue, and this is the boundary of red and again, so red and orange and orange. Okay. And these are the two labels, and you can see the level of noise. Okay. So if I don't do that multiplication by 10, the original level, so what do I get? So you get still the same optimal variable, but this is the true variable. You can see the level of noise is different. So I could do somewhere in between. Let's say if I do 5, you still have noise. Let's see. Okay, so you can see you can control the level of noise by scaling the parameters. Okay, we're almost out of time. Let me do it quickly and then it might not actually work. So I define a loss, and yeah, it's going to take me a while to do it. But the idea is that now I have a true model. Now I generate like a new model, which I'm going to train, and I'm going to define a loss and then do a gradient descent on the loss. And hopefully the output will be close to the true model. Okay.